In Lab 3 we will create a new project that uses the LSM6DSO inertial measurement unit. The sensor will be configured to detect the acceleration pattern associated with steps, and to maintain the corresponding step counter. When steps are detected, an interrupt is generated. The firmware will wait for the interrupt to happen, then it will read the step counter from the sensor, and it will print its value on the serial terminal. LSM6DSO inertial measurement unit is made of an accelerometer and a gyroscope. The peak power consumption is as low as 0.45 mA at 6,666 samples per second. The sensor has an I3C interface. The sensor has also an auxiliary SPI interface which is typically connected to controllers for optical image stabilization. The sensor has a large first and first out buffer. It is made of 3 kilobytes of memory but can typically hold as much as 9 kilobytes of data when lossless compression is enabled. Data can be processed on board by embedded finite state machines. Up to 16 finite state machines can run concurrently to detect specific sequence of events and generate the corresponding interrupts. The interrupt generation logic is rich of features. It can detect a freefall condition, which corresponds to an acceleration close to zero. It can detect changes in the orientation. It can detect single or double taps, which correspond to acceleration pulses with specified intensity and timing. In this lab we will be using the embedded step counter. As in the previous lab, we will need to configure PB8 and PB9. PB8 and PB9 are the pins of the microcontroller that are connected to the I2C communication bus. This bus goes from the microcontroller to all sensors on the expansion board. Also, we will need to configure PB5. PB5 is the pin of the microcontroller that is connected to the interrupt line coming from the LSM6DSO inertial measurement unit. Let's begin. Launch the STM32Cube IDE. Click on the File menu. Select New and then STM32 Project. The IDE may try to check if some update is available. If the network settings are not configured, the IDE will ask to configure them. You can safely cancel the operation as we have already downloaded everything we need. Wait for the IDE to load the list of microcontrollers and development boards. Then click on Board Selector. In the search field type L476. L476 is the part number of the microcontroller on the Nucleo board. A short list of matching boards will appear. Select the Nucleo L476 from the list. Click on the Nucleo L476 item to confirm, then click on Next. Type the name of the project and then click Finish. Accept the default initialization for all peripherals. At this point the Cube MX embedded in the Cube IDE may try again to check if some update is available. If the network settings are not configured, the IDE will ask to configure them. You can safely cancel the operation as we have already downloaded everything we need. Wait for the project to be generated. When you see the graphical representation of the microcontroller, you can zoom in with the mouse wheel. Look for PB8 and PB9 on the top edge of the microcontroller. PB8 and PB9 are the pins of the microcontroller that are connected to the I2C communication bus. This bus goes from the microcontroller to all sensors on the expansion board. Click on PB9 and select the I2C1 serial data line function. Click on PB8 and select the I2C1 serial clock line function. PB8 and PB9 are now connected to the internal I2C1 peripheral. The color of the pins is yellow-orange because the internal peripheral is not enabled yet. To enable the I2C peripheral, go to the left panel. Click on Connectivity. Then click on I2C1 to open the corresponding mode and configuration window. In the window, select I2C from the pull-down menu. Note that the color of the pins becomes green. The color becomes green because the internal peripheral to which they are connected is now enabled. Now zoom out and look for PB5 on the top edge of the microcontroller. PB5 is the pin of the microcontroller that is connected to the interrupt line coming from the LSM6DSO inertial measurement unit. Click on PB5 and select GPIO external interrupt line number 5. The pin becomes green immediately because the internal interrupt controller is already enabled. However, we need to enable the interrupt for line number 5 so that the corresponding handler can be executed when appropriate. Go to the left panel. Click on System Core. Then click on NVIC. This is the Nested Vector Interrupt Controller. Click on NVIC to open the corresponding mode and configuration window. In the window, click the checkbox to enable the interrupt for line number 5. We are now ready to bring in the additional software from the XCubeMOOC package. Click on Additional Software near the top of the window. Click on the arrow corresponding to XCubeMOOC. First, we need to bring in the low-level drivers for the sensors on the expansion board. Click on the arrow corresponding to board extension and select IKS01A3. IKS01A3 is the part number of the expansion board. Second, we need to bring in the high-level application code. Click on Device Application. Applications can be found in the pull-down menu. To be able to see the full name of the application, you may need to adjust the width of the columns. Select the pedometer application that uses the embedded step counter in the LSM6DSO inertial measurement unit on the IKS01A3 expansion board. Finally, click OK and you are back to the main window. We have brought in the drivers and the application code, but we need to enable them. Go to the left panel. Scroll down. Click on Additional Software. Then click on STMicroelectronics XCubeMOOC to open the corresponding mode and configuration window. In the mode window, click the checkbox to enable the expansion board drivers and the application code. In the configuration window, we must select from the pull-down menus the pins that the application must use. The first item is the pin associated with the interrupt from the MOOC sensor, PB5. Then the pin associated with the user button on the Nucleo board, PC13. We need to specify the output serial peripheral, asynchronous UART number 2. We need to specify the input communication bus, I2C1. Finally, the pin associated with the green LED on the Nucleo board, PA5. We can now save the project, which will trigger the actual generation of the code. The code is now generated. Expand the core folder. Then expand the source subfolder. Double-click on main.c. You will see the generated code. User code can be added between sections marked as user begin and user end. User code added inside these sections will be kept when the project is regenerated, while user code added outside these sections will be lost. We can now build the project and create the binary. No other project should be open while we build this project. Click on the hammer icon on the top. In the console, you can verify and monitor the compilation process. The compilation should be completed with no warnings or errors. Now it is the time to connect the Nucleo board with its expansion to your computer by plugging the USB cable. When the board is connected, we can flash and debug our application. Click on the bug icon on the top, then click OK on the pop-up window. The firmware binary is programmed into the target microcontroller and run. The debugger will halt the execution at the first breakpoint, that is at the beginning of the main function. Click the play button to go past the breakpoint and let the firmware run. Now the firmware is running. Let's check the output. Minimize the Cube IDE window and launch the Serial Terminal Emulator, TerraTerm. Remember to connect to the serial port associated with the Nucleo board. Remember to set up the serial port so that it works at 115,200 bits per second, 8 bits, no parity, 1 stop bit, no flow control. Time to move the board. Shake the board at a regular pace. You need to simulate at least 10 consecutive steps before the counter is updated. This threshold is programmable. It is used to reject false positives. As soon as the threshold of 10 is exceeded, the counter is updated by adding 10, and then it is updated after every new step. Whenever the counter is updated, the corresponding interrupt is generated. When the firmware on the host microcontroller receives the interrupt, it will read the step counter from the sensor, and it will print its value on the serial terminal. Note that no computation is performed on the host microcontroller. Step detection and counter updates are performed entirely by the sensor. This offloads the host microcontroller and allows for a significant power saving. When you are done, go back to the IDE and click on the Stop button to stop debugging. We can now close the project. Right-click on the project name and select Close. Thank you.